Okay, it's going to be the lesson on 4.1 horizontally launched projectiles. So the do now question says you shoot a ball horizontally off the edge of a table. At the same exact time and the same exact height, you let go of another ball that draws vertically. Well, which ball hits the ground first, or do they both hit the ground at the same time? Right? That question, well, you're gonna have most students think that the ball that launches horizontally hits the ground first because, well, it launches with a speed, right? It launches with a speed, so whatever is going the fastest will hit the ground the first, hit the ground before the other one. But that's not the case, right? And as you see here, and I would have done this in class. Actually, I did do this in class, but this is essentially a video representation of what's happening, right? So you have a ball launched horizontally and you have a ball that's just dropped. And you see that will both essentially hit the ground at the same exact time. So they take the same exact time to really just go down to the ground. And then why is that, right? We're gonna talk about why as we go through these slides. So the world right now, it's 3D, right? There are 3 dimensions in our world, right? There's in math class you should learn that there's an x-axis, right? So there's an x-axis and there's a y-axis and then there's a z-axis, right? So 3 positions in space give us 3D. We don't really go too far into 3D actually in physics. We actually never touched 3D at all in high school physics. The most we go up to is 2D, right? So this would be a 2D. Right? So there's a y there and there's an x there, and so this would be something in 2 dimensions. Now, for every object in 2D, we can essentially define information for it in the x and y axis. For example, distance. Distance traveled in the y-axis. So let's take a look. If you kind of just graph each of these points, let me use a different color. Let me use this green right here. Right, if you kind of look at the vertical distance that the ball is traveling, this is true for the red and yellow ball, right? And so you will see that, well, this object here, essentially your vertical distance traveled each second increases each second, right? So here you don't really have as much vertical distance traveled, but as you go down, as you continue going down, you'll see that, well, my vertical distance increases as the object goes down. And if we say that my vertical distance, let me use a different color now because we're running on a different background. And if my vertical distance increases here, or if my vertical distance increases here, then we can say that my object here is accelerating. We can say there's acceleration here, right? My object is accelerating. My object is getting faster, right? My velocity of this object is changing because clearly you see that you travel a greater distance as the ball each second. So it is accelerating, it is increasing. And so that's our vertical distance, right? That's our vertical distance. But let's take a look at our horizontal distance traveled for the yellow ball. And so let's take a look at our horizontal distance. So here, 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 and here, and you take a look at our horizontal. And then when I say horizontal, I mean literally that, right? So your horizontal, this is your horizontal, horizontal, horizontal. So you see the middle there, the horizontal, right? So the horizontal. And you'll see that, well, my horizontal distance traveled each second is essentially the same, right? It's constant, right? So I travel in the horizontal distance, so horizontally, my horizontal distance, my horizontal distance is essentially constant here, right? My horizontal distance is constant. And if we travel the same distance each second, we can say that, well, my velocity is constant as well, right? So we also have a constant velocity here versus the vertical direction, where my velocity was increasing in the vertical direction, but in the horizontal direction, my velocity is constant. And so this is really just further proof here that, well, we can take velocity in two directions, right? Because clearly in one direction, in the vertical direction, my velocity was increasing. The distance I traveled vertically was increasing, but the distance traveled horizontally remained the same. And thus we say that, well, my horizontal velocity is constant. So again, it's further proof that, well, we can definitely for sure classify things in two dimensions. We're gonna watch part of this video, right? It kind of communicates the idea of something like this in visual form.
Therefore, projectile motion is made up of a horizontal and a vertical component. The horizontal component is constant velocity, and the vertical component is uniformly accelerated motion, with a downward acceleration that has a magnitude of 9.81 meters per second squared. Now, let's combine them all. Again, notice how the x direction has a constant velocity and the y direction has a uniform downward acceleration.
So you can see across this video that, well, that something here is made up of an x and a y, right? So as this object is moving in a parabola, it's going up and then down, right? So at the ball in the middle, well, it not only does it have a vertical motion, it's not only going up, but it also has a horizontal motion. So something is definitely made up of two things, right? There's two dimensions here.
Motion. Therefore, projectile motion is made up of a horizontal and a vertical component. The horizontal component is constant velocity, and the vertical component is uniformly accelerated motion, with a downward acceleration that has a magnitude of 9.81 meters per second squared. Now, let's combine them all. Again, notice how the x direction has a constant velocity and the y direction has a uniform downward acceleration.
Yeah, as you can see, as an object is moving in the middle, well, not only does it go up as a vertical component, but it has a horizontal component.
Now let's add velocity vector components in the x direction. Bobby, what should the velocity vector components look like in the x direction for the ball as it moves to the right?
Well, in the x direction, the ball has a constant velocity to the right, so the vector should have the same magnitude the whole time and be pointed to the right.
Correct. So as the ball moves to the right, we can freeze the ball at several locations and add the velocity vector in the x direction, which will always have the same magnitude and therefore the same length arrow.
And you can see, well, it travels the
Now, let's look at just the upward motion of the ball in the y direction. Billy, what should that velocity vector look like?
Well, we know the ball must start with an upward velocity in the y direction, and because the acceleration is downward, that velocity will decrease as the ball goes upward. So the magnitude of the velocity vector will decrease and it should eventually reach 0 at the very top.
Correct. And Bo, what about the velocity vectors of the ball in the y direction as the ball is going downward?
As Billy pointed out, at the very top in the y direction, the ball has a velocity of 0. So the ball will have an initial velocity of 0 and accelerate downward. So the velocity will have an increasing downward magnitude as the ball goes down.
So again, in the y direction as the ball moves upward, that velocity will be upward and decrease in magnitude until it reaches 0 at the very top. As the ball moves down, that velocity will start out at 0 and increase in magnitude and always be downward. Now, let's take a look at projectile motion. Remember, projectile motion is a combination of the horizontal and the vertical components. So we can now take those horizontal and vertical velocity vectors and add them to the projectile motion video. Those velocity vectors are the x and y components of the resultant projectile motion velocity vectors, which we can now add to the video. And there are all the velocity vectors for projectiles.
So you can see there that again, it is made up of x and y. So now we go into independence of vectors, right? So again, the first question here says, does my acceleration due to gravity affect both the x and y directions or only one direction? You can see here that my acceleration due to gravity really only acts in the y direction. You can say that because, well, you don't really see your horizontal velocity changing, right? Your vx, your v sub x doesn't really change. It's essentially 20 meters per second every single time and point in this image. So we can say that my horizontal velocity is not changing. Well, if my horizontal velocity is constant, there is no acceleration here. Whereas in the y direction, clearly you have an acceleration. Clearly your velocity is changing as your object falls down. So my acceleration due to gravity really only acts in the y direction. You can see that my y velocity is the only velocity that's changing, my vertical velocity. And so the second question here says, well, what is the initial velocity of the object seen to be in the y direction? We know my initial horizontal velocity. We know what that is. It's 20 meters per second. But well, how far is it? What was the initial vertical velocity? How fast is it falling down initially? Well, the canyon is not falling downward until it leaves the canyon. It's being fired horizontally, which means that it has an initial horizontal velocity, which is 20 meters per second. But the ball, the canyon, the object does not leave the canyon, or rather, it does not does not start falling until it leaves the canyon. If it does not start falling until it leaves the canyon, you can say that, well, my initial velocity in the vertical direction, VIY, my initial velocity in the vertical and the y direction is going to be 0. Right? It doesn't have an initial vertical velocity. It only starts increasing its speed once it actually leaves the canyon. And this is something you really can assume for this topic in Regents physics. Right? Alright. So again, we can separate vectors into x and y. Right? So something like velocity would have a velocity in the x direction and would have a velocity in the y direction. And velocity in the like distance in the x direction, dx, right? You would also have a distance or displacement in the y direction. You would have acceleration in the y direction as well as the x direction, but really the only variable that doesn't have a specific direction associated with it is time. Time itself belongs on both sides. Now, when we do these formulas right here, we never mix them. We never mix x and y. You'll see that on these formulas here, that these all have the y notation within. There should be a y there, but it's not included. And you'll see on the x side, well, there's always x here. Now, we can never mix these variables, right? For example, if I try to write this first equation here, you cannot do this, right? You cannot mix a y vector and an x vector, right? You can't do axt, right? This is illegal. You cannot do this. You're mixing x and y, which is definitely not possible. You cannot mix two different directions. It has to be either only y or only x, never both. Actually, let's analyze the equation on the right-hand side. Now, because again, you don't have any acceleration in the x direction, you don't really have any acceleration there. And because you have no acceleration in the x direction, because again, acceleration due to gravity only acts in the y direction, my entire term here will be 0. Because 0 times anything is 0. Which means you're only left with the left-hand part of this equation, which then becomes this equation that you see here. This is the only equation we can use in the x direction for this topic. 4a. So let's do a practice problem, right? So really the first step here is, what's going on? Oh. Yeah, really the first step here is, well, we need to figure out our knowns, right? And so to figure out our knowns, we need to figure out, well, we do either x or y direction, and we have to put them in, categorize our knowns in either x or y. So essentially the image is saying that, well, you launch the object with a velocity of 20 meters per second east horizontally. So you're essentially launching it horizontally, which means my velocity in the x direction is 20 meters per second. We also see something else here. We see 100 meters. We can say that, well, that's my height. Or what we can essentially say is that, well, my displacement in the y direction is negative 100. It's negative 100 meters because anything below the origin, and rather it's going downward, but if it's going below the origin, essentially anything below 0 is negative, anything above 0 is positive. Essentially, we're treating where we start as 0. You can also just look at it as if you're going downward, well, your displacement will be negative, all right? So you can think of it that way as well. We also know that we're looking for time, right? That's what the question wants, and time really just belongs on both sides. Now we have to make 2 more assumptions, right? We need 2 more assumptions that we can make here. One is that, well, if the object is falling, we can say that, well, the acceleration due to gravity in the y direction is negative 9.8 meters per second squared. And we can say that, well, because it's being launched horizontally, we can say that, well, it doesn't really have an initial vertical velocity, right? My initial vertical velocity is 0. It doesn't start falling until it leaves the cliff, which means that my velocity in the vertical direction is really just 0. And these 2 things are really just something you can always assume for the y-axis in Regents physics questions in this topic 4.1. And this is just really something you can always do. So we want to know what our time is. We want to use the y direction here. We should use the y direction to solve for time. That's something we can do in Regents physics. You can just say that's pretty much always the case, or most likely the case. So the only formula we can use is this one. It has everything we need, right? As dy, as viy. We're looking for t. We have a, and we're looking for t. So essentially, all you're doing is you're plugging things in. So you're gonna do that. dy is negative 100, 0, ay negative 9.8, t squared, negative 4.9, t squared, this gets you 20.4, and then you do square root this, and then you get 4.5 seconds. Okay, and this is your time. This is your time. So let's move on to the next question, right? And something really just students kind of sometimes make a mistake on. Actually, I would say that students make this mistake a lot, is that when they're plugging these things into this equation, they kind of just instead of putting 0 for my initial velocity in the y direction, right? Instead of putting 0 here, they see, well, my velocity in the x direction is 20 meters per second, and then they do that, right? Then they do that. But you cannot do this because, again, you cannot mix x and y. They do this and then they get the wrong answer, or rather, they don't know where to go from that point on. So it's very important, again, that you do not mix your x and y. So this question right here is 4B. It kind of leads off the other question. So the question now says, well, how far from the base of the cliff, and the base of the cliff is over here, how far from the base of the cliff does the object land? Right, so essentially you're looking for d sub x. So you're looking for d sub x here, right? You're looking for that. And you got time from the previous question, which is 4.5 seconds. And you know that your velocity in the x direction is 20 meters per second because, again, you launch it horizontally at 20 meters per second. And the only equation you can use in the x direction is that one, right? So that's the only equation you can use, right? So dx is equal to 20, 4.5, and now we get 90 meters, right? And so 90 meters, it travels 90 meters away from the base of the cliff. 4C is solved the same way as 4A. The only difference here is the distance in the y direction. So let's do it again, x and y. We launch it horizontally at 15 meters per second. It also says in the problem, horizontal speed. It lands on the second platform. If it lands on the second platform, well, we can say that my distance in the y direction, my displacement in the y direction, essentially is negative 2.4. Really, that's really the difference between 6 and 3.6. And because, again, you're going downward, it is going to be a negative number. We're looking for total time. Time belongs in both directions. And again, I told you guys you can just assume that in topic 4.1, my initial vertical velocity is 0, and my acceleration in the y direction is this. Okay. And we're going to use the same exact formula, actually. Because this formula, again, has the everything we want. Just going to plug things in. This is 0, negative 9.8, t squared, negative 2.4, negative 4.9. That's going to give you this somewhere around here, somewhere around 0.49, and then you square root both sides, and then you get 0.7 seconds, and that's t. That's t right there. All right. All right, let's do this. The diagram below represents a ball launched horizontally, projected horizontally. So the first ball here, this is a different type of question. It's like essentially a conceptual question. So the first ball gets launched horizontally at this speed, right? So that's Vx. It lands a certain distance, and we're going to call that dx is d. Right, so that's going to be that. Now t, you're given your time. You're given your time. And the question then says, well, you launch a second ball. You launch a second ball, and the second ball is launched horizontally at a a velocity of 20 meters per second. And then the question says, well, determine the distance the second ball lands from the base of the cliff in terms of d, right? So essentially you're looking for dx in terms of d. And we know that, well, from the do now question, that no matter how fast you launch something horizontally, all objects, if you're launching them from the same height, will reach the ground at the same exact time. So the time it takes for both objects to reach the ground is exactly the same. Let's do this. Let's solve for dx here. Right, so dx is, I'm replacing dx with d. That's essentially what that is. Vx is 10, and then t is t. And if we do the same exact thing here, dx is equal to vx times t. I get dx. We don't know what dx is yet. Vx is 20, and then t is t. So if we know that d is 10t, right? The distance that the first ball travels is equal to 10t. And the distance that the second ball travels is 20t. How can we get this in terms of d? Right? One thing you guys have to realize here is that your second ball travels 2 times further horizontally than your first ball. This is double this. And well, if 10t is d, then what's 20t equal to then? 2d. This is 2 times the original value. And so this is your answer. This is in terms of d. This is your answer right here. Okay? Okay. Okay. So let's do 4e. 4e is a conceptual question. 4e says projectiles launch horizontally from a height of 65 meters. Right, so this is 65 meters. Launched horizontally at 35 meters per second. And they want to know, well, after it's fallen 25 meters, so probably somewhere around here, right? Somewhere around at this point. Well, what is my velocity at this point right here? Again, guys, you have no acceleration in the x direction. And what we talked about from the previous slides is that, well, my velocity in the x direction is constant. There is no acceleration. And if my velocity in the x direction is constant, then this is my answer. My velocity doesn't change. We talked about it in one of the previous slides. So for F, this is really the same exact concept. If player throws the ball horizontally, which statement best describes the ball as a motion after it is thrown? So after it's thrown, right? So my horizontal velocity remains constant, but because we are accelerating as we fall downward, we do have a vertical acceleration due to gravity. My vertical velocity will change because again, it is accelerating. There's an acceleration in the y direction. There's just no acceleration in the x direction, but there is an acceleration in the y direction. Right, so the only logical choice here that kind of corresponds with this is C. And that's the answer. That's this lesson, right? That's the lesson. All right, bye-bye.